So one of the last topics we'll investigate in this current unit is just kind of something additional. So I call this additional topic number 2 in this unit, and it's going to be about a special theorem. So I thought we'd start by discussing and returning to the big ideas, theorems that you need to know for the AP exam. Most of them won't be on this unit test though, and for you guys this year, that's your final, right? It's just differential equations, but it is going to have a couple of these kind of problems on there. So we'll do our last new section tomorrow. So big theorems on the AP Calc test. We're going to learn about the last of those big theorems today. You guys should know like 3 or 4 other big theorems that you used to study by, because next year we're going to be taking the exam. So, what is one of the big theorems that we've learned in calculus this year? And I'm not going to like write all the different consequences of those theorems, but the fundamental theorem, and it's really 2, right? But let's just put that in there. So the fundamental theorem. Sounds big. It's fundamental. It's really kind of 2 though in 1. So parts 1 and 2. So definitely want to be super comfortable with those fundamental theorem going into the AP exam, or it's going to slam you. What else? I'm thinking farther back in the class, kind of the beginning. Definitely. That's the other big one. So I would say the mean value theorem is definitely also a big theorem that we should be comfortable with immediately by the time we're ready to take the AP exam. So I'm not going to talk about all these different theorems today, I'm just listing them. And another one these are probably your 2 big ones. This guy and this guy are smaller, but they're still going to be included in my list of the big theorems. What is the other one that says if you're continuous and differentiable, in other words kind of connected, that if you have a value in between a and b, there has to be a y value between f of a and f of b. Well, of course Calc used. So, yeah. That one's been a while for us at this point in my class. Before you're ready to take either the Calc AB or BC exams, you need to know these inside and out, be incredibly comfortable with them in a variety of different circumstances. So today we're going to learn the last one, and that is what I like to call, and I kind of made this name up myself because it seems to fit, and I like to have a name tag to remember stuff. It helps me. I don't know if it helps you, but I call this one the Inverse Derivative Theorem. Okay? We're just going to do one example with it today. So it's kind of just a smaller tool that's useful in specialized circumstances like the one that we'll be presented with. So the inverse derivative theorem says, okay, you got to be a differentiable function. You got to like have an inverse thing. If you're not invertible, sorry. Some functions are like that, but most of them are invertible. So, and f inverse also, the invertible function has to also be differentiable. Okay, somewhere we're interested in. If that's true, then this kind of provides you an alternative tool besides directly calculating the inverse of another function and then taking that guy's derivative. You can kind of get around that with the cleverness of this theorem. It says if you need the derivative of an inverse function, because sometimes finding an inverse is difficult. You know what I mean? We'll see an example like that in a second. So what if you can't find the inverse easily? What if it's difficult, or what if it's really a little bit impossible to do for you? Then you can find a way around that by saying, well, the derivative of the inverse function is just the reciprocal, or 1 over the derivative of the original function with this guy plugged in. So it's just an alternative curve around something that could be inconvenient. So I think it's pretty easy to see how it's used with a concrete example. So here's an example. Here's a function, a cubic polynomial. So the first question we have is just an algebra 2 question. So it says, what is f inverse when x equals 3? So if I asked my algebra 2 students that, they're just beginning to, well, they just this year began to work with inverses. So most of them would probably go, well, I need to plug 3 into the inverse. I don't have the inverse yet. Oh, but I learned that this year. So they'd go like, inverse, what do you do to get the inverse from the original? You switch x and y, right? We should all remember that. And then you try to solve for the new y, right? The problem with this one is going to be, Y cubed and y, like you could go like this at least, right?
Pull out a y.
That's a great idea, pull out a y.
Somehow you're gonna have y on both sides.
And if this was quadratic, we could like do some kind of fancy completing the square to get it by itself, but it's not even quadratic. So I think what we'd have to do at this point is like way beyond our algebraic capabilities probably. It's possible, but it's super inconvenient to do that. So at this point we'd be like, well, this sucks. So I think we're going to take a more abstract conceptual approach. That really is kind of running into a brick wall. So can we just do this with still, by the way, no calculus, just algebra 2. I think that it really helps to visualize things like this, and I'm going to be expecting to see this on most of your problems, and it's just like this on the exam too. So let's think about f, and let's think about f inverse as just points, because really the first question they asked is just 1 point at a time. So they asked, if you put 3 into f inverse, what do you get out, right? So they're saying 3 in, and the thing they really want to know is what comes out, right? What's special, again, about a function and its inverse? What did I do to try to solve for the entire function at a...
The x of f is y of f.
So I can say, oh, this... and that are the same. The x's and y's are switched. So another way around this question for such inconvenient areas or functions like these is instead of trying to find f inverse and plug 3 into it to get what you want, take the thing you already have.
Plug 3 into that.
Don't put 3 into that.
Set it equal to 3.
Set it equal to 3 and solve for the thing that you want. And it'll be the same as that. Okay, so I'm going to be expecting to see these little coordinate pairs. Man, this is important for higher level math, number 1, but it's also important to being easily successful with this. This should be a really easy theorem to use, and it's all about if you're thinking about what an inverse is precisely, and I think this is really going to help you writing them as coordinate pairs. Okay, so I'm going to say, well, I'm going to set f of x equal to 3, and now solve for that. Now, of course, that is what kind of function? It's a yucky cubic function. It's not quadratic, it's degree 3, right? So I'm going to set it to 0 by subtracting 3 this way. And I'm going to just solve that with my calculator. And you can do that on your assignment, okay? So I'm going to go to my calculator to solve that one for me. I'm just going to do it graphically. So let's come over here to our calculator and solve it graphically. So y equals, looks like 0.25 x cubed plus x minus 4. I'll zoom standard it. And there's a nice cubic curve. It looks like it crosses at about 2. I'm just going to calculate it. So calculate 0, left, right. Yes, convenient. So it turns out that this is 2 because I solved it with my calculator. So that means that this is 2, which answers my question, because they wanted to know f inverse of 3. What is that? That is equal to 2. Okay, so there's an algebraic way to solve that problem. The thing we want to do is build up to being able to take a derivative in this kind of situation. So the second question I had for us to finish up for today is, write it down. And this can be written different ways. Notation can be different. So same problem, except instead of looking at the inverse, only the inverse, I wanted to look at the inverse's derivative. You could write it like that, with that notation, or with this kind of notation, like prime for Mr. Newton, right? So I think I'm just going to use the theorem on that one. So the theorem says that this guy evaluated at 3 will be equal to what? Theorem says it's going to be equal to 1 over f prime f inverse of 3. So that's 1 over f prime, and f inverse of 3 is something that we already did. What was it? It was 2. So if you're on a problem like this and it doesn't like give you a lead-in algebra 2 types question, if it just says this right away, what's your first thing going to be to do? Your first thing that you need to do is go, just like we did, go f inverse. They said f inverse of 3, so you need this. So then you should go like that, and then you should go, oh, so I can figure out what this is and put it in there. And then that thing is the thing that I'll need. Okay? So it should be that simple. So this should be pretty easy because f prime for this function, super easy, right? It's just, oh, you already got it? I'm going to show it though, Parker. So f prime for this function is just 3/4 x squared plus 1, right? So f prime of 2, like we needed, is 3 times 4 over 4 plus 1, which is 3 plus 1, which Parker has determined to be 4. So this is 1/4. Now there you go. I never needed to actually compute the inverse. I have this workaround little inverse derivative theorem. The key with the inverse derivative theorem is that it kind of only works pointwise, and I'm going to put that in its title for you guys just for your notes. This is kind of a pointwise theorem. I think you can actually extend it to beyond just one point at a time, but that's how we're going to want to think about it, at least for now. Is that it's kind of like one point at a time, and we should always see for every one of your problems those points. The last thing I want to say is in your assignment on the worksheet, some problems are going to ask you to like verify. So some problems will give you an easy function instead of like a cubic. They'll give you something much easier, and they'll say compute the derivative at a point the direct way, so like find the inverse, switch x and y, do it the direct way, and then confirm that it's the same thing if you use the theorem. So some problems in there are going to ask you to kind of do it the old school way without cleverness and confirm it with this new clever machine that I've just introduced. I'll see you next time.
Old potatoes.